Thank you very much. Welcome, everyone. As mentioned, my name is Lily Noy Harbottle. I'm going to talk to you about medtech, specifically medical robotics for lung cancer. So, get started. Okay. Let's start with a thought exercise. So, without raising your hand, I would like everyone to just stop and think. How many of you know someone who has been impacted by cancer of any form? Maybe neighbor, coworker, friend, cousin. How many of you know someone who was impacted by lung cancer? Okay. So for most people, that's where the conversation ends. But for us, engineers, scientists, developers, problem solvers, the human impact is just the beginning of a systems level challenge. So, just in Greece alone, lung cancer is the leading cause of mortality for men. It is the third leading cause of mortality for women. According to data from the World Health Organization, over 22% of all the cancer deaths in Greece are due to lung cancer. So this makes it a primary health concern, and it's one that hopefully we could address with every tool at our disposal. I also wanted to show you another study. This one was from a hospital in northern Greece. It tracked patients for over 18 years. And out of a really large sample size of over 15,000 patients, a little over 5,600 were confirmed lung cancer cases. And the ratio of men to women who were confirmed was higher for men than women. The ratio was 2-to-1. So it means that men were more likely to be diagnosed with lung cancer than women in this particular study. So what this means, and comparing it to the rest of the world, globally, every year, about 2.4 million new lung cancer cases are diagnosed. That's just an estimate. I've seen higher. But what this also means is that the global surgical market size by the year 2032 could be about 16 billion euro. So this means that not only are people trying to solve the problem, it is an area of great opportunity for problem solvers. So where does that bring us to today? We're talking about Python, about engineering, and science. So the question is, how do we empower clinicians? Because it's not just about statistics, it's about lives, and it raises several critical questions. We know usually with cancer, the earlier you find it, the better. There are better chances of survival. And nowadays, with medical robotics, we can make these types of diagnoses and procedures less invasive and more accessible to a lot of different people. So again, how do we empower clinicians? So I have a poll, and I'm going to drop this link into the channel in our shared Discord for this room. So this is a thought question because I would like to know who's in the room and answer to the best of your ability. What do you think is the most transformative impact of medical robotics? There are a lot of ways to answer this question. What is the most transformative impact of medical robotics? Someone who is already familiar with the concept might already have a strong idea of what this could be. And the truth is, depending on your profession, depending on your experience in healthcare, all of these could be correct answers. So hopefully it works on your screen that you can answer this next question. What is the biggest hurdle in getting a robotic system to see inside of a human lung? Thank you for everyone who decided to participate. Real-time fusion is an absolute concern. Happens all the time in the field. Lighting and contrast issues depending on your camera. Lack of a clear pathway through the lungs, that's absolutely a challenge, and image distortion. These are all really good insights. Thank you, everyone. Okay, let's move on to the last question. You kind of already saw this. What is the most difficult engineering challenge in medical robotics overall? Okay, great. So we'll wrap up the poll. Thank you for everyone who participated. These are all different areas of concern depending on your experience within software or robotics and controls. Or if you're a product owner, you'd be concerned with regulatory hurdles, UI, UX, human interaction. That's a completely different field. So these are all areas, depending on your background, that might be of the highest concern to you. But these are all areas where different experts within their field need to integrate and meet at the table in order to come with a realistic solution. So that was my attempt to understand who's sitting with me in the room today. So thank you for participating. All right, so let's go back to the talk. We talked a little bit about what was the motivation for medical robotics in a Python conference. So right now we'll get into a deep dive, and at the end we'll get into next steps. Okay, so the core problem that we're trying to solve is locating a tiny abnormal spot that may or may not be cancerous in the lung. And we have had ways of doing this through X-rays, MRIs, CT scans for years. We know this works. But imagine if you go to the doctor because you detect something strange going on in your lungs. Your doctor says, okay, let's take some scans. The scans come back. Traditionally, in the old days, you would go into an operating room for a biopsy. In a biopsy, the traditional way is the doctor would cut you open, take a sample, patch you back up, and you'll stay in the hospital recovering for weeks. And that's a lot of downtime in the hospital, just recovering. So when we talk about what about today, modern times, well, for the last over 25 years, minimally invasive robotic-assisted surgeries have become more and more widespread and popular throughout the world. For example, there's a company that has held over more than 15 million lung cancer biopsies across 69 countries in the last 25 years. And the idea behind a minimally invasive surgery is that instead of making a huge cut into your body, the doctor can either make a really small cut or no cut at all. So you can imagine that if the doctor can do a biopsy without cutting into the human body, then that means that you would have less downtime in the operating room, in the hospital after your operating session. So we're going to quickly explore how we're going to go from simple CT scans, which are 2D, to something a little bit more elaborate, such as the 3D airway reconstruction. And this is not brand new knowledge. You could search this online. You can find open source code for this. But a robot integrates a lot of different technologies. So we'll briefly brush over these areas, but I wanted to show this image. So we're taking 2D slices. Think of it, analogy would be like a book. You have multiple slices, and from all these 2D slices, you can construct a thick book. But what do you do with it afterwards? How is that useful for a surgeon in the operating room? Well, you want to construct a 3D model. So you're going to need a huge data set. You're going to need a really good algorithm, and you need to test it. So I know this is a little blurry. This is another way. On the right-hand side, you have 2D slices. Left-hand side, that is what the camera would see inside the human body when it goes down the trachea. And then this is the 3D rendering of the model of that person's lungs. And this ball, that's the suspicious mass that may or may not be benign for cancer. So when we talk about visualizing model output, the model's output for a lot of machine learning models, it's more than just a coordinate because it's almost like a moving target for the physician. Even if you go into a procedure and you're put to sleep, the human lungs are extremely intricate, and everyone's lung set is unique and it's not symmetric. Therefore, your model needs to be extremely robust and well-trained. And especially with hospitals, which may or may not be open systems, you might not have internet connection. So your model is going to sit on a robot in a hospital that may not be with the most recent software. So your software needs to be pretty much perfect. So I'll briefly get through an example of the system. We have different ways that Python and just software code in general is used throughout the entire cycle of this. So when I say pre-op, that's the part where you get a bunch of MRIs, CT scans, whatnot, which is prescribed to you by the doctor. The idea is that you can get these scans, and the doctor will feed into the algorithm, the robot, and from there, we'll have algorithms that create a 3D rendering of your particular lungs. From that, a plan is created for the doctor to navigate down your lungs through its bronchoscope, and the physician could customize the plan. So what that means is once it's decided that you will go into procedure, it's called intra-op, and that's where this robot in the middle comes in. This is one of many examples of what's out on market of different types of robot-assisted surgeries just for lung cancer. And then finally, afterwards, there's the post-operative analysis. So for intra-op, we'll briefly get into what are we talking about. So bronchoscope goes down the trachea, and it's navigated by the physician, and it's steering itself through tension wires. And this blue thing goes down the throat. And it's so thin, it's thinner than a pencil. And the tension wires navigate down through your lungs. So not only that, this bronchoscope is attached to the cart through the attachments. From there, we have the tower, which are the brains, which controls all the movement. And we also have the controller that the physician is using. So if you notice something here, the physician still has eyes on the patient. They have eyes on the camera that's going down the lungs. They have the 3D rendering. They have the pathways to guide them as they steer down the human lungs. They have the CT scans for each area where you're traveling down the human airway. So when you think of all this software code and its millions and millions of lines of code, when we talk about Python, this is sort of like a mirror of what would go on during a surgery. The real-time telemetry, depending on what you're using, would help the doctor to make sure that they're not getting too close to one side of the lung wall and they're going straight to the pathway that leads to the potentially cancerous mass. So these are some of the many libraries and packages that are really important for this type of work. So DICOM stands for Digital Imaging and Communications in Medicine. It's similar to an international standard for medical images and its related information. There are already existing ways to unpack images, to transfer them, to track them. There are also a lot of different ways to handle everything from the imaging processing as well as to the data handling and the visualizations. So we briefly did a case study about what goes into this entire robotic system, but there's still a lot of work to be done. It usually takes years for any clinical drug to be approved by a local government. It's even harder for any medical robot to be approved. So when we talk about lung cancer as a global problem, but also an area of great opportunity, the idea is that when we talk about the software that goes into it, we have to be diligent about what we're using, and we have to understand it well enough to address problems that we talked about earlier about the data fusion, as well as the UI, the camera issues, also end of life. And then obviously, as more and more conversations come up about usability of AI, we've been using algorithm for years. It's just nowadays it's called AI. But within the world of medical robotics, it's heavily regulated. And oftentimes the regulations are stricter than AI regulations as they exist today. So the idea is that as problem solvers and engineers are going about your work and doing your contributions, this is where it goes towards. And hopefully in some time in our lifetime, those really serious statistics that we showed for lung cancer in the world get a little bit better. So thank you, everybody. I really appreciate you hanging on with all the technical